What did the Earth look like hundreds of millions of years ago? When did the first trees originate? What did they look like, and what effects did they have on their ancient biosphere? That's not the question that 19th century stonecutters were wondering as they blasted apart the hillsides of peaceful upstate New York. In the sleepy town of Gilboa, workers were cutting sandstone blocks to build a dam. Little did they know that under their very feet were buried clues to our planet's past.
In 1869, Gilboa stonecutters discovered odd stone bulbs in the layers of sandstone they were quarrying. They were cut from the stone and collected, and in a matter of years, geologists had identified these bulbs to be the roots of ancient fossil trees. Today, we know a great deal about the morphologies and behaviors of these enigmatic trees, based on inferences made from the fossils left behind. So what does it mean to be a forest? Today, forests are ecosystems with hundreds of working parts. Plants and animals interact with each other every day and with the earth itself. But scientists have only identified 3 different species of trees at the Gilboa site. So what can a seemingly small handful of information tell us about the past? Well, the answer may surprise you. Before we look at the big picture, we're going to need to get our hands dirty and see what these fossils can reveal. In order to squeeze every bit of information we can out of these rocks, I think we're going to need to talk to an expert. And I know just the guy. Let's go! We're here today to visit my friend Marty Pendleton, a fossil expert on the Gilboa rocks. During the Devonian, New York was located on the equator near the coastline of an intercontinental seaway. From the lithology of the rocks, we can tell a lot about the environment. Alternating layers of mudstone and sandstone indicate that there were periods of calm where the mud could settle out, punctuated by storms where sand was washed into the forest environment. Let's go see what Marty has to say about these rocks. Marty, good to see you, man.
Hey man, what's up? Alright, dudes and dudettes. This is a stump from the Gilboa fossil forest itself. Let's take a closer look. Sweet. The first thing you might notice about this is that it has got a bulbous shape. It's kind of weird, right? But when we compare them to modern tree root systems, we can make inferences about the environment of the Gilboa forest, which was similar. A swampy coastline environment.
Right on!
See these squiggles? These are the roots. You can actually see how they all radiate outwards from the stump. For a while, these stumps were all we knew about the Gilboa trees. But scientists recently found a 6-meter-long tree trunk and its crown of frondy appendages, whose characteristics resembled those found on the Gilboa tree stumps, so closely that they had to be the same tree. So we now know that these Gilboa trees could reach heights of 8 meters, which is incredible. We originally thought early trees were much smaller. Scars along the length of the trunk indicate that the tree probably shed its frondy branches. This is further confirmed by scientists also finding detached and randomly arranged branches in bedding planes slightly below the one the trunk was found within. In some fossils of these fronds, we can even see sporangia. Altogether, the image we get of these ancient trees is that of a modern tree fern with large fronds.
Thanks, Marty. That was great. Now that we know a little bit more about these trees and how they behaved, we can look at them as pieces in a much larger puzzle.
That's what scientists in 2010 were hoping to do when studying a newly cleaned bedding plane at the quarry. The site contained around 200 large dimples, interpreted to be root mounds of the Eospermatopterus fossils that had originally been removed from the site. But these scientists found 2 other types of trees during their study.
In order to get into the ecology of the forest, let's go talk to my good friend Vivienne.
There are 3 types of trees at the Gilboa site. The first is the Eospermatopterus. the famous Gilboa tree. The traits of these trees, such as their great height, are found in many tree types throughout history. But the traits cannot all be traced back to the same common ancestor, so it's clearly a homoplasy, an independently derived character. The second tree, Anurophytalian rhizomes, took scientists by surprise when discovered. Anurophytons are an extinct plant genus, thought to be basal members of the progymnosperms, the probable ancestors of seed plants. They're also classified as rhizomes due to their creeping habit. These trees were found growing horizontally across the forest floor, reaching as much as 15 centimeters in diameter and most likely exceeding 4 meters in length. Some of the tree fossils were surrounded by numerous unbranched organs that we believe to be their roots. Many stem fossils form arcs around Eospermatopterus root mounds, but a number of them appear to end quite suddenly at the rim of the mounds. This indicates that the Anurophytalians interacted with the already established upright Eospermatopterus trees, possibly even winding around them and using them for support. The last tree is the arborescent lycopsid, a tree-like member of the Lycopodiopsida class, which are club mosses. There was only one found at the Gilboa site, preserved horizontally. The sample was 11 centimeters in diameter and around 4 meters in length. 4 or 5 smaller axes were found nearby and may have been attached to the main trunk, but we aren't totally sure about that. The trunk and branches are all covered with the same distinctive pattern of attachment scars. This finding is important because it predates the previous earliest lycopsid tree in North America. What's so exciting about all of this is that the forest was much more diverse than we originally thought, which changes our understanding of how the ecosystem operated. These trees shed their frondy leaves and small branches, and this kind of litter may have encouraged the development of a detrital-based arthropod ecosystem, which is certainly something we see in later Devonian forests. There may have also been a limited marine ecosystem present, based on ostracod fossils found at nearby locations. These trees were affected by their location on the coast. The sizes they reached were more likely related to the rates of growth and frequency of reproduction permitted by storm disturbances than by regional environmental factors.
Understanding the fossils is the first step to unlocking the mystery of Earth's ancient forests. Thanks to Marty, we have a pretty good idea of what the rocks can tell us. The information extracted from these rocks allowed paleoecologists like VIVIENNE Farthing to study the interactions of these species and grant us a better look into the window of the past. But how do we take it a step further? We know what we'd see if we walked among the Gilboa trees, but what ramifications did these Devonian forests have on a more global stage? The answer to that question must be explored with an interdisciplinary approach. Paleoclimatology and geology are two fields with the tools to tell us what we need to know, and my buddy Rodney is an expert in both.
So we want to know what impact Middle Devonian forests, like the one found at the Gilboa site, had on the Earth. Well, these forests shaped their regional landscapes, but they may have had an even larger impact than previously thought. Let's dive in. The Gilboa Forest is part of the Manarkill Formation, located in the Catskill mountain front. The geological records show that the formation records the westward progradation of a coastal plain as a result of the uplifting Acadian Mountains. What is especially notable about the Manarkill Formation are the interbedded paleosols, which serve as incredible paleoclimate records. Additionally, the Plattekill Formation below and Tully Limestone above were used to constrain the age of the Manarkill beds to about 386 million years. This points to deposition during the Gavetian period, a faunal stage of the Middle Devonian that was defined by biostratigraphic indicators such as ammonoids, conodonts, and ostracods. Using evidence encoded in the paleosols, such as grain size, overburden calculations, and the geochemistry of rainfall acidity, it was determined that Gavetian forests in the Appalachian Basin grew in a variety of environmental niches. These environments ranged from deltaic coastal plain swamps and proximal fluvial environments to distal, well-drained upland floodplain conditions. Based on root evolution and communal forest structures, it has been theorized that Middle Devonian forest development had a huge impact on basinal floodplain and coastal environments, resulting from their carbon cycling and organic sedimentation. These paleosols further suggest that the fluvial and deltaic presence of Gavetian forests influenced continental weathering, vastly heightening sediment and nutrient delivery to marine systems. With these ecosystems revolutionizing continental weathering, new theories have cropped up about the impact this might have had on the Earth itself.
So what can we infer from RODNEY's conclusions? During the Phanerozoic, the biomass of marine consumers increased. Size and fleshiness of individual specimens has been widely documented to have grown as the eon progressed. Additionally, metabolic activity and demand rose concomitantly, suggesting there was some new factor energizing the oceans. An intrepid theory holds that the increase in the ocean's energy budget was a result of the greening of the planet, that is, the rise of plants on land. Models show that there is a lag in the radiation of these new high-energy environments moving offshore. So, for example, the shallow offshore marine environment becomes energized before the continental shelf does. This is consistent with the theory that land flora would provide nutrients into the ocean by way of continental weathering and fluvial ion transport. The arrival of trees boosted sequestration of carbon on both land and in the ocean. Silicate weathering enhanced carbon storage in soils by consuming carbonic acid. Groundwater carrying these ions and nutrients promoted carbonate precipitation, algae growth, anoxic conditions, and carbon burial at sea. Further evidence of these forests' impact is the global reduction in atmospheric CO2 levels, which potentially initiated glacial periods in the Paleozoic.
So you might be thinking to yourself, what more could we possibly want to know about the Gilboa fossil forest? Well, there are actually many more avenues of further study that could prove rich and rewarding. For example, we've talked about how this was an environment periodically battered by intense storms. Such disturbances represented major constraints for ecosystems. Notably, plants that have adapted to disturbed habitats are generally small in size. We have records of Gilboa trees 8 meters tall. This is an intriguing case of plant evolution that deserves further investigation. We know that Devonian trees were modular, where multiple fronds formed a crown. This body plan lends itself to shedding detrital branches and accumulating a serious litter mat on the forest floor. But how much did this dynamic affect the atmospheric carbon budget? In concert with terrestrial flora-instigated silicate weathering systems, the carbon budget of the Earth would have been supremely altered. There is still a lot of work to be done on what the greening of the planet did, well, for the planet. The theory of a more energetic ocean as a result of the rise of terrestrial plants introduces a lot of questions about the ramifications of this paradigm shift. If the oceans were inundated with nutrients, it only follows that the photic zone became more diverse and full of life. Conversely, this would have led to anoxic deep waters and the reorganization of the deep water zone. Scientists were also surprised by the discovery of a wide variety of morphologies at the Gilboa site due to the general consensus that these Devonian forests were not complex. Plants in these forests had similar morphologies and adapted to the same environmental conditions. This presence of 3 distinct plant types in the Gilboa forest is the first direct evidence that some early forests contain widely divergent groups of plants. This discovery will hopefully lead to the reinvigorated investigations of Devonian forests as diverse ecosystems. So how could these plucky little stumps have had such far-reaching effects? Well, by asking hard-hitting questions like that that'll get us on the right track to understanding the world that we live in. Thanks for coming along today, and I just want to say, see you next time.
Ronnie Dorf?